Okay, the final presenter this afternoon is in the corporate slots is Jonathan Lintott. Jonathan is Managing Director of Anderson Caledonia, a major UK sterilisation and testing company. He started his career in industry over 25 years ago as a steriliser engineer in Asia and has also worked in the USA and many parts of Europe as well. Jonathan has a Masters in Engineering from Oxford University and is a lecturer on sterilisation and process control at the University of Limerick. Last year, Jonathan was invited to train the new Saudi FDA regulatory body on sterilisation, microbial testing and biocompatibility. Okay, Jonathan?
Thanks very much, John. Can you all hear me? Great. Great. Don't turn that one off. Yeah. Just. I think that one's off, is it? You're on. Great. Wonderful. So, firstly, I'd like to say thank you to Ian, if he's about. 5 years ago, Ian's work at Lattice started us on a long journey, and I'm going to tell you a little bit about that journey today with adding a bit more about qPCR. So the first thing I'd like to ask is, how many people have had a PCR test for COVID? How many in the room? Ooh, that's a lot. 70, 80% of you. How many of you would say that you knew how that test got a result? How many of you understand qPCR? Ooh, about 10, 15%. Okay, well, I'm going to try and go through it a little bit in 10, 15 minutes and try and get you all up to the same level. So let's start. qPCR. Introduction to qPCR. Polymerized chain reaction. All started off in Yellowstone National Park, where a guy was hanging out in the hot tubs, and he found an enzyme called TAC, or Thermobacillus aquatis, which was basically an enzyme. And what enzyme is, it's an enzyme that can operate under high heat, and it's a building block for DNA. So when we are using PCR, what we do is we have a primer, we have a DNA template which needs to be copied, and the primer finds a DNA template. We then have the nucleotide bases, which are the building blocks. We have an enzyme which builds a new DNA, and then we have a buffer to make sure it all works together. So, 3 stages to PCR. Firstly, denaturing. You take a DNA, you break it open. You use heat to break it open. Second stage, annealing. So you take the opened up DNA, the primer finds the target DNA, and it joins together. And finally, extending. The PCR enzyme eats up these combination of amplicons, which are the combination of the primer and the template DNA, and they make a new strand of DNA. And so they copy, and you continue copying. And every cycle, you get more and more copies. Double-stranded DNA, denaturing, you're breaking open the DNA, 94, 95 degrees Celsius. Then the annealing stage, your primer finds a target DNA. I kind of feel like this. I was giving this chat to my brother, who's a doctor, and he said it's a bit like, kind of like a nightclub. You know, you've got a bunch of guys there and a bunch of girls there, and they're all trying to match up. They all match up, and then the next stage is extending. They all go home, and they have a baby, and that's the next stage. That's the way I think about it. That's the way my brother thinks about it. That's what you get with a surgeon. Anyway. So that's PCR process. You're creating copies, DNA copies. But how do we find out how many copies you created? Well, the next stage is you've got a fluorescent dye. And the fluorescent dye is found with a fluorometer. So let's see how that works. So these are machines, a couple of different types of machines, and I think we saw one, the little one in the Amazon. There's some bigger ones like Applied Biosystems, which is one of the ones that we've got. We've actually got one of the baby ones too. And what these do is they basically have a fluorometer in them which can detect fluorescence. So when they see fluorescence, they've identified that there's DNA. So the more it fluoresces, the more it picks it up, and when it reaches a certain level, it goes, great, we found that DNA. So in other words, you get fluorescence growing as your DNA is copying. You get more and more fluorescence, and at a certain point, you hit a certain threshold level, which is known as the CT value, and that CT value shows you've got the DNA. And the machine goes, bingo, we've got it. And typically what you'll find is that for the first 10 cycles, you're not going to get anything. Then after 10 cycles, you can start getting a positive. But when you get a positive at low cycles, maybe 10 to 20, that means you've got an awful lot of the target organism. Then you go on to 20 to 30, you probably got less, and then finally up to 40, you do 40 cycles. And so if you're getting a CT value in the 30 to 40s, you probably started with a very small amount of DNA. Now, it's not directly equivalent, so you can't fully take the CT value and say how many organisms you had at the start, but it's an indication. So I remember a few months ago, one of my workers came in and said, Jonathan, he said, I'm not feeling well. I said, oh, what's up? He said, I don't know, I've got this cough. And I said, Stuart, hold back. What's happened? He said, you know what? I had my brother in to do some work, and he's just tested positive for COVID. I said, brilliant, Stuart. Get out of here. Go home. Unfortunately, he gave me COVID. So I thought, okay, well, this is bad news, and I was going to get vaccinated in a week's time. So got it before I got vaccinated. I said, okay, so what am I going to do? Well, I'm going to have to sit home, so I'm going to play. I'm going to at least try testing myself every day to see what happens on my CT values. So what I found was the first day, my CT value went from 0 to 17 in a day. Brilliant. I've got COVID. Cheery things. Next day, actually didn't feel too bad. Don't worry about it, I'm still alive. Next day, I was feeling a bit sick, a bit tired. My CT value, 17 again. Kept going for a whole week. Felt better after 3 days, but my CT values kept going at about 16, 17 for a whole week. And then after a week, they started going up, 22, 25, and then 0. So in other words, it was just after a week, it began to peter off, and then it went just back to 0 and had no CT value. So essentially, it seemed to work. It was quite consistent. Although I felt good after about 2 or 3 days, it took about a week before your CT values came down, which is quite interesting. So you can still have COVID in your mouth, even when you've got past the disease. So, probe, fluorescence. We were just talking about fluorescence. How do you get the fluorescence? So essentially, you have what's called a probe. This is one of the approaches, but the main approach that's used. And what that probe has, it's a piece that's built into the DNA, which has a reporter, which is a fluorescent dye, and a quencher, which stops a fluorescent dye fluorescing. When it gets eaten into the DNA probe, the new piece of DNA, the quencher gets released, and so it can fluoresce. So essentially, the probe ties into the new DNA, the quencher is released, and it starts to fluoresce. So these probes are wandering around, just like the primers, looking for this target DNA and adding into the amplicon. And that's how we get our fluoresce. And that is our little DNA polymerase building the new pieces of DNA. Anyone? Okay. Anyone got any questions on that? No, please don't. Ronan will give you some more details. What I'm going to do now is try and show you a little video of this all in practical process. Okay, is the video? Do I just? Okay. So I'm going to show you this all in a 2-minute video. Oh, nope. Is the video? We got the video. Okay, got the video. So when we start the process, and this video is one where we're doing testing. This one's COVID testing. Okay. Good, it's going. Okay, so we start the process. We got the sample. We just mix it to make sure it's consistent throughout the sample. We then do an extraction process, which is purifying and concentrating the DNA, or in this case, the RNA, because COVID's RNA. So we take a sample of the sample of COVID, which came in a viral transport media. We then put it into a machine. You can do manual extractions. We're doing semi-automated extraction here. So essentially, the samples are put into the extraction machine, which concentrates and purifies the RNA. We then take the samples out. So we now have purified RNA. We then take it, we add it into the master mix, which contains the primers and the probes, the buffer solutions. We mix them together. We then put a film across the top to prevent any contamination from one well to another well. So you can do 96 wells at a single time. We take these 96 wells, we then put them into the PCR machine. Firstly we do the mixing, just to properly mix them. And then after the mixer, we put them into a PCR machine. And the PCR machine will typically take about 90 minutes. And if you want to stop there, sorry. Can you go back and just stop there? Yeah, just stop there. So this is kind of like the report you get. One of the interesting things, this one's COVID, is, as you can see, is you don't just necessarily get a single gene that we're looking for here. In this report, we've also looked for the S gene. So in this case, they're all negative. It was quite recent, so we've got mostly Omicron, which is negative on the S gene. So one of the benefits with qPCR is you don't necessarily only need to look for one piece or one gene or one type of DNA. You can actually have now, for instance, primers which will identify COVID, it will identify influenza, and it will identify RSV all on the single master mix. So we're having primers which can identify multiple different organisms or genes at the same time. So moving on. So what is the use of qPCR? Why are we going to use it? What's the benefits of it versus culture methods? So we had a look at, for instance, result turnaround. A qPCR takes about 3 to 4 hours from start to finish to do a cycle. Culture methods take about 3 to 30 days, so it's very fast. Microorganisms, as we talked about, qPCR finds all microorganisms, not just viable but non-culturable, and viable but non-culturable. So it finds everything, whether it's alive or dead. Culture methods mostly find bacteria and funguses and viruses, but the cell culture method for viruses is quite complex to do. Not many people can do it. Viability, the culture method finds only viable. qPCR finds both viable and non-viable. And the test result, whilst the culture method will provide you a total viable count, qPCR just typically finds you the presence and the absence and that CT value, which gives an indication as to the amount, but it isn't quite directly relevant. Can't be quite correlated to the TVC. It just gives an indication. Just talking about viable but VBNC organisms is that not only are there organisms that might get damaged and therefore you cannot culture them, but there are also organisms which we haven't been culturing even at the start. In other words, the typical culture methods don't develop them. And so there's certain bacteria which qPCR will find, which our culture methods will never find because they're not designed to find them because they don't cover all the microorganisms that exist. So where are we with qPCR? So as you can see, we've obviously done a lot of COVID testing. We've got a UCAS accreditation now for qPCR testing, and we're extending our qPCR testing. We have taken on the mycobacteria as well. About 3 years ago, we started doing mycobacteria. And I was going to give you some of the results and some of the data so you can see what's happening. We've done maybe quite a few more samples in Isofarm. This is just a sample of some of the results we've got. What's quite interesting is, for example, it's a north-south divide with qPCR testing. The north is obviously far ahead of the south in new technology advancements. Scotland leading the way, Jimmy. So qPCR testing, we've had, this is a sample of just some of the this is just an extract of some of the samples we did last year. And what it shows is that we're getting somewhere around 30% positive. Now, a culture method, we were talking about 5%. With qPCR, we're now up to 30% positive, which means is that almost 1 in 3 of the samples we get on a new install or even a routine is testing positive. That's a very high count, isn't it? Means our system is very sensitive. We're picking up pretty much everything. What is good, because I know you're all looking worried. I can see you, Larry, you're looking worried. What's good is retests. The rates are going down, and retest rates are now, in some 100% negative, but mostly our retests are sitting at 5 to 10% positive. So when we are getting positives, they're doing remedial action. The second test that we get is typically negative, which means is that remedial actions that are being undertaken by the manufacturers or the service companies are eliminating the mycobacteria. So in other words, we're finding it and we're eliminating it. And actually what we've noticed is the guys we're working with are getting better and getting rid of it. And one of the things you can do now is typically, if you take the time from the first positive to the second result and the negatives, it's typically less than 2 weeks. In other words, you can find a sample, do remedial actions, do a second test, find it's negative, all within 2 weeks. Whilst with the culture method, you're still waiting 30 days before you've even got a result. So essentially what it's allowing us to do is to reduce mycobacteria. And I think that trend will continue. I think we'll get to a stage where almost all retests will be negative. In other words, I would also think the 30% is going to come down, because once people know how to get rid of mycobacteria, they will get much better at eliminating it out of the system. So mycobacteria PCR testing is widely used in the UK, especially in the Midlands and North and Scotland. Scotland's going for it. Test data has shown an initial positive rate of around 30%, and the positive rate for retest has been going to under 10%, which shows that remedial action is working and getting rid of mycobacteria. So what's the pros and cons of qPCR? Well, pros, speed. It's quick. As you can see, it's not a long process. It's about 3 to 4 hours. Throughput. That machine can process that you saw Jean, who was working on, does 100 samples in 3 to 4 hours. We can typically process up to 1,000 samples a day on just that one machine. Sensitivity, it's highly sensitive. We pick up everything. I mean, if you get the extraction right, and the extraction techniques, which is I think what Ian was talking about, are getting better and better, because with mycobacteria, breaking them down, finding all the different species, once you get through that, the sensitivity is very, very sensitive. Scale of quantification, you get an indication. You're not going to get the same count level as TVC, but you're going to get an indication from your CT value as to how much DNA you have. And finally, reproducibility. As I found out when, for instance, I had my COVID and I was doing samples, day after day, I was sampling, getting the same result, always getting positive, never had a negative in the middle. It's a very reproducible process. And we've seen that actually once or twice. We had someone with mycobacteria, they took a test, they go, oh, we don't believe your result. They did it again. Guess what? They got exactly the same result. They just, yeah. So we told you had mycobacteria, and guess what? You do. What are the downsides of qPCR? Well, firstly, it's kind of expensive. These machines are still not cheap. It's going to come down, but it's still quite an expensive process. Reagents aren't cheap. Again, you know, the manufacturers have been making a lot of money out of this with COVID and things like this, and the reagents are still quite expensive. So it's not as cheap as culture method, but I think it will come down in time. Sample preparation and loading time, you do need trained people to do this. This is a process which is still, you need a very technician who's skilled in it. It's not for everyone. You've got to be, you can get errors. You can get inhibition, you can, as you're nodding, things can go wrong, put it this way. It takes time to get it right. Inhibition is one that we struggled with when we first did PCR a few years ago, a lot of inhibition. And it's sensitive to errors. If one mistake, and you basically have to restart and redo all your sampling. So it's One that's, you've got to spend a little bit of time getting it all right, but once you get it right and you've got a process, it works beautifully. Every time, same thing. Great.
Thank you, Jonathan. We've got a couple of minutes. Any questions? Marianne, because I cut you off last time.
Just a really quick one.
Sure.
What is your limit of detection?
So it depends on...
So on the mycobacteria.
So mycobacteria, what would you reckon, Ronan? Sorry, my line manager's there. I think we pretty much detect less than 100.
In what quantity of sample? Per mil? So less than 100 per mil. So in 100 mil, you're about 1,000. Is that right? So if you...
I mean...
Okay.
In essence, what we've done is, and we're validating it for our UCAS accreditation, so we are probably detecting way below what you can buy as a sample to detect. So it depends as to what you use as your sensitivity, as the sample you can get to create, to do a test. But you know, I think we're picking up very low. I don't think we're missing anything almost. Our feeling is. I think what the EQAs, what's the EQ, are there EQAs at the moment, Ronan, on? Yeah, there are EQAs. I think they come in at 100. So the EQA for mycobacteria, I think, is 100. And we're you know, that's what we're finding. But I think we're probably picking up a couple of mycobacteria.
Also, at that point, sorry, we concentrate the sample beforehand. So we don't have a 100 ml sample and extract.
No, of course you concentrate. Yeah.
Concentrate it down first before recovery, which we work with an enzyme company and we must nail that.
Thank you.
So we concentrate. Yeah.
Actually, can I answer a question?
Not a problem.
Yeah. You're going to ask me a question right now?
Yeah, just for a change, yeah.
You were training me on this.
I think it was Karen that asked about the 109 species types and how do we know that we're actually nailing all of them. We don't design primers ourselves. That's we leave that to cleverer people. But the design company that we work with, at the time of producing the mycobacteria primers that we use, they actually, it was based on 95% of the NCBI sequencing bank. So we know that 95% of the sequences that they had on record were incorporated into that primer design, which is also the name of the company. So yeah, I think that gives a good confidence interval on, you know, species, all relevant species within our remit.
Any more, Karen? Oh, sorry, go on, Shalusti.
Yeah, sorry, Salusi?
Yeah, we send sample to you. Is there any reason why you do not offer PCR for Pseudomonas and endotoxin?
Absolutely. Well, Pseudomonas, absolutely no reason. We're adding additional, as we speak, we've added Legionella, or we're adding Legionella to our UCAS accreditation. We're kind of like splitting between also adding some of the more diagnostics things at the same time. But Pseudomonas, I think, is something relatively easy for us to add. You know, we can be quick to do a samples of that. Endotoxin, I think it's interesting. Endotoxins, what do you reckon, Ronan? I mean, theoretically we can find endotoxins, but I don't know if is there a primer for endotoxins? Oh, sorry.
Surely looking for the gene, so what you'd then be talking about would be a pan-gram negative, I assume. Because you're looking for a gene, you're not, and there is, you know, the endotoxin is in the cell wall, so you're looking for that gene. So
Yeah.
it would probably be a pan-gram negative of some sort. you'd have to look for.
You'd have to look for, yeah. I mean, it's a bit more complicated than endotoxin, which is why I'm asking, because I'm not sure that we've actually thought about it yet.
Karen, did you want the last one?
I was just going to ask you what sort of CT values you're seeing in the real samples, both for the first positive and for the second positive, and do you see sort of 30s and
Yes.
for the second?
Yeah, I mean, the CT values for mycobacteria are mostly in their 30s and 20s and 30s. 20s to 30s. We don't get low, we don't get highs, so they're typically, we would think, small levels, mostly.
Hi, it's just a comment. The Pseudomonas is very quick result as well in the culture.
Sure.
It's just 24 hours really, so it's not that big of a problem. And we, most laboratories have UCAS accreditation for the culture of Pseudomonas, so that isn't something that I suppose brings such an advantage with PCR as it does with Mycobacteria
And
or
Legionella.
Legionella, for example.
Yeah. It's a fast, yeah.
Okay. Okay, thanks, Jonathan. Thank you for that. Very interesting.
Thank you.